Okay, finally for the grad students, here is problem number 9 in homework 2. And this one says we're going to consider a 100 megabit per second Ethernet link. And we're going to ask how long does it take to transmit 0.252 megabytes worth of data at this rate. And supposing that the speed of signals on the wire is 200 meters per microsecond, how long is a bit on the wire? How long, that is in meters, is a bit on the wire? And how long is the entire file on the wire? So here I'm talking about how long in space, not in time. Suppose the wire from another transmitter's, so the wire from the transmitter to the receiver is 85 meters long. What is the total time to transmit the file starting from the first bit sent to the last bit being received? So let me do this problem for you. So we're going to consider a rate of 100 megabits per second. Okay. And we're going to consider a file size n of 0.252 megabytes, which is 252 kilobytes, which is 252,000 times 8 bits per byte, and this is 2.016 times 10 to the 6th bits. Okay, so 2 million bits, more or less. And what we're going to write is one of the basic equations of data transmission, and that is that the rate is equal to the length of the file, the number of bits to send, divided by the time it takes to transmit. Okay? And this is the rate in bits per second on the left, and the numerator is bits, and the denominator is seconds. So the units work out, bits per second on both sides, and I can solve for the time it takes to transmit. This is n over r, which is 2.016 e to the 6th, all divided by 100 e to the 6th, which is about 1/50th e to the 6th, or 20 e to the 3rd. 1/50th, yeah. Or about 1/50th of a second. The e to the 6th is canceled. 1/50th of a second, or 0.0216 seconds, or 21.6 milliseconds. Yeah, about 20 milliseconds there. So that's how long it takes to actually transmit that file, to actually spit it out. Okay? For part B, we're given that V is 200 meters per microsecond, which is the same thing as 200 times 10 to the 6th meters per second. A microsecond, remember, is 1/1,000,000th of a second, so we get 1,000,000 bits per second when we had 200 per microsecond. And the length of a bit, another sort of fundamental equation, although more for fun than anything else, is the length of a bit is the velocity times the time it takes for a bit to be sent out. And so this is 200 times 10 to the 6th meters per second times the time for 1 bit. And the time for 1 bit is 1 over the bit rate. One's in bits per second, the other one's in seconds per bit. And this is 1 over 100 e to the 6th, or 10 to the minus 8th, or 1e minus 8. And so 1e minus 8, and I get 2 meters. Okay, so each bit is 2 meters on the wire. For part C, it says now the length of the wire is 85 meters. Calculate the total time. To transmit the frame. And what we're going to do is we're going to draw a diagram that shows time. And it shows our two stations 85 meters apart. And at some time t equals 0, we're going to send our first bit out. Okay? And it's going to take us a certain amount of time to transmit that file. So that's TTX. Okay? But then that bit is going to move through space and finally land over here. And so the whole file is going to go through like that. And the slope here is given by the velocity, because it's the time axis and this is the space axis, x. Okay? And so you can label the time to transmit, or the time for that first bit to fly across between the wires, as t propagation time, t prop. And so we have t transmit down here. Also, the amount of time it takes to actually receive those bits coming in on the wire is the same amount of time it took to send them out onto the wire. And so we can label a bunch of these times. Here's where the first bit was sent. Here's where the first bit received. Here's where the last bit was received. And here, some other funny time is where the last bit was transmitted. Okay? But basically, we can calculate the propagation time because it's equal to the length of the wire all over the speed. And that's 85 meters all over 200 times 10 to the 6 meters per second, giving us 0.425 microseconds. Okay, and we've already calculated the time it takes to transmit the file, and that was up here, and that was 21.6 milliseconds. And so now we see, okay, the amount of time it takes to propagate is much, much less, a tenth or 4/10 of a microsecond, than it does to actually transmit the bits, which is 21.6 milliseconds. And so the total time is T transmit plus T prop, which is 21.6 milliseconds plus, and 0.425 microseconds is 0.000425 milliseconds, or approximately 21.6 milliseconds. Okay, so I hope that helps. Here we have a space-time diagram showing the propagation. This is kind of like the train problems in your physics class. Hope that helps.